Okay, so that whole thing I just went through with the heating and the latent heat of fusion, latent heat of vaporization, it's all kind of wordy. I have a little graph here that can kind of explain it as well. We'll go through it fairly quickly. So we're going to start at minus 20 with no heat, and then we're going to raise the temperature. So to go from minus 20 to 0 for 1 gram of ice requires 20 calories. So it would look something like that. Now we're at 0 degrees, but we're still at ice at 0 degrees. We have to break bonds. So we have to add in 80 calories to break bonds. When we add in those 80 calories, the bonds break, but the temperature doesn't go up. Okay? So that's the phase change. That's latent heat of fusion. Okay, so now, after adding in 100 calories total, we are sitting with water at 0 degrees. Okay, if we want to raise the temperature of water, 1 gram, it requires 1 calorie for every degree. So to go from 0 to 100 requires another 100 calories. We're now sitting at water at 100 degrees. This is the boiling point of water, but to actually get it to boil and break all of its bonds, we have to add in the latent heat of vaporization, which is a huge amount of energy, 540 calories. We then break the bonds. We now have steam at 100 degrees. If we want steam at 200 degrees and we have a gram of it, we have to add in another 100 calories. So total of 840 calories, 220 just to change the temperature, but 620 to change phase. What happens if we go the other way? Okay, let's start with steam at 200. And now the steam releases its energy. Okay, it needs to cool off, right? In order to cool off, it has to get rid of some of its heat. So it releases its heat into the environment. So to drop 100 degrees, what does it have to do? It has to get rid of 100 calories, right? And it does that. So as steam drops from 200 to 100, there's a gram of it, it's going to give off 100 calories into the environment. Basically the air around it, or if it's in contact with other rocks, could be the rocks around it. So if it gives off 100 calories, what do we have?
Steam at where 100?
Steam at 100 degrees, right? If we want it to condense into water, what does it have to do? It has to form bonds to come together as water, right? And in doing so, remember when we went the other way, it required 540 calories? In this case, to form water, it's going to give off 540 calories into the environment. So it has to lose 540 calories in order to become water at 100 degrees C. Okay, if we want that hot water to cool off and freeze, what do we have to do? It has to get rid of some heat, right? To drop it down to its freezing point, there's a gram of it, it's got to drop 100 degrees, it has to give 100 calories off into the environment. Now what do you have? Now you have water at 0, right? To freeze it, has to form bonds. When you form bonds, that releases energy into the environment. In this case, it's going to release 80 calories. Now you have ice at 0 degrees, and if you want to cool off ice, you just have to get rid of a calorie for every degree, for every gram that you want to drop it. So if you have a gram, want to drop it 20 degrees, you have to get rid of 20 calories. So my grandparents, when I was born, my grandparents didn't have electricity at their house. They lived in the northern part of Michigan, so they didn't have refrigeration. But my grandma had vegetables all winter long from her garden. But she didn't have a refrigerator. And it's cold up there. I mean, it's damn cold up there. How did she keep her veggies from freezing? There wasn't enough room in the house. Couldn't just keep a house full of vegetables with all the kids running around. This is what everybody did back then, and it's all based on latent heat. My grandma knew about latent heat, even though I think she only had like a 7th grade education. What they would do is, they didn't have basements, but they had a crawl space under the house. So what they would do is they would enclose that crawl space with wood, and they would put a bunch of barrels of water down there. Okay, and then they put all the vegetables down there too. Now, as the temperature starts cooling off, right? What's the water in the barrels going to do as it cools off?
It's going to release heat.
It releases heat into that crawl space. And at what point does it release a lot of heat? When it freezes. So when it starts to freeze, all this heat starts coming out of the water, and it basically insulates that crawl space. So all they would have to do is just go down every couple of days, and if it started to ice completely over, they just break up the ice to expose more water, and then as that froze, it would give off this tremendous amount of heat. And they were able to naturally refrigerate without freezing the bejeebers out of their carrots and beets and stuff. They would stay right around 32 degrees. Even if the outside temperature was minus 50, the crawl space would stay right around 0 because all the heat coming out of these big buckets of water they would stick under there. It was basically like sticking a mini heater underneath, because when the water froze, it gave off all this heat to the environment. So we're going to use this concept when we start talking about melting rock here in a minute, but I wanted to kind of go through this with you with a substance you might be a little more familiar with. Okay, so going the other way, 840 calories get released into the surroundings. So when you heat things up, it requires heat. When you cool things off, it gives off heat. Okay, so going back to what we first talked about, in order to melt something, in this case rock, because we're going to make magma, because this is a class in volcanoes, we need magma. We need heat in order to raise the temperature of rock to its melting point, and then we need a whole bunch of heat to break those bonds and actually create the melted material. Now, every mineral that we have in rock has a slightly different heat budget. Slightly different specific heat, slightly different latent heat. But the bottom line is it requires a ridiculous amount of heat to melt rock. It's really hard to melt rock. If it wasn't hard to melt rock, we would have volcanoes everywhere. We'd have volcanoes in Iowa, but we don't. We only have volcanoes in certain environments on Earth. And that alone should tell you it's really difficult to melt rock and get it up to the Earth's surface. Or it'd be everywhere. So to kind of summarize where we are right now, it takes a lot of energy to heat up rock, and you have to heat it up to really high temperatures because those bonds are strong. And then once you get it to that really high melting point, you got to have a whole bunch of extra heat to break the bonds. And think of it from the other way too. If you do get melted rock, when it cools off, it gives off a tremendous amount of heat. And it takes a while for melted material to give off its heat. I made that mistake once and only once. We're in Hawaii, there were some active lava flows. We walked up to them with our rock hammers and we were pulling little bits off with the pointy end of the rock hammer, just about maybe this much. So I pulled off a little glob of hot red lava and let it cool by the side. And about an hour later, I had gloves on, because you always wear gloves out there. I picked it up and stuck it in my pocket. That was just a really stupid idea. It burned through my pants in about 3 seconds, left a nice old welt on my leg. I mean, it was still hundreds of degrees C, even though it was completely black. And even though there was only a few grams of it, it just takes a long time for it to get rid of that heat, for the temperature to drop to a part where a human being could pick it up and not burn themselves. So lava flows, think of a whole big lava flow then. How long is it going to take a lava flow to cool off? So there's a lava lake that formed in the 1950s in Hawaii called Kilauea Iki. It's about 1,000 feet deep. The thing is still molten in the middle today. You know, it's been 60 years and it still has a molten core. It takes that long for it to lose its heat. So these are long-term processes just because of the energetics required to heat stuff up and then for it to cool off as well. All right, so in order to get melting, I think the whole point so far is that we need a lot of heat. So where does this heat come from? Well, we know the Earth is hot inside, right? Where did all that heat come from? Well, a couple different sources. One is that there's probably heat left over from when the Earth first formed as a planet. So what we know about planetary formation is that in order to get a planet size Earth, you have to bring in a lot of smaller space particles together. When they collide, they usually collide with a lot of kinetic energy. That kinetic energy is transferred into friction and heat. And in fact, when the Earth first formed as a planet about 4.6 billion years ago, there were probably so many of these impacts that the Earth was completely melted for a while. The heaviest material then moved to the core of the Earth gravitationally. All of the heavier metals like nickel and iron, and the lighter materials like silica sort of buoyed to the top buoyantly. And the outer crust cooled, and a lot of that heat is trapped inside the Earth. And it's estimated that today about a half to a third of the current heat loss from the Earth is probably due to this original heat from when the Earth first formed as a planet. So we have lots of heat in the Earth. In fact, if you go to the core of the Earth is about as hot as the surface of the sun. It's dang hot down there. About 20 years ago, I got to go to the bottom of the Homestake gold mine up in South Dakota. It's the deepest gold mine in North America. About 10,000 feet, so about 2 miles down. It takes about 20 minutes to get to the bottom of this thing with a high-speed elevator. And as you go down, it gets hotter and hotter. It was 123 degrees at the bottom. That's only 2 miles down. And it went from ambient up here, average, 40, 50 degrees, to 120 some degrees down there. But remember, the core of the Earth is about 4,000 miles down. So about the distance from LA to Boston. So just think, if you keep increasing the heat, how hot that's going to be. So the inside of the Earth is really hot, no doubt about it. There's a lot of heat down there. But again, it's probably not enough to melt things up here at the surface. So again, these impacts create enormous amounts of heat. On some planets, they're enough to initiate massive melting. If you look at the moon, we have giant craters. And in a lot of those craters, the craters are filled with lava. And just based on the timing of things, it seems like that lava formed during the impact. So just one big impact can melt a lot of rock. So when the Earth first formed as a planet and melted everything, that's a lot of heat. And we still have impacts today. When your planet has an atmosphere, a lot of the space junk that might impact your planet actually burns up as it goes through that gaseous envelope, the atmosphere. But if you have a planet or a body that doesn't have an atmosphere, like Mercury or our moon, those impacts can just slam into that planet without the atmosphere filtering them out. And like I said, you can look up at the moon and see craters that are filled or partially filled with melted rock. So in some places, it's still an important process today. Here on Earth, Venus, there's enough of an atmosphere to keep away a lot of the large impacts. But every once in a while, something big gets through, like 65 million years ago, big enough to initiate a mass extinction. Another source of heat is radioactivity. We have a lot of radioactive elements in the Earth, and when they go through their decay process, they give off heat. Different elements give off different amounts of heat. So the four most abundant long-lived radioactive elements are listed here. You have uranium-238, uranium-235, thorium-232, and potassium-40. So that second column shows how much heat is produced. And what you'll notice is that uranium-235 is about 5 to 6 times more heat productive than the next closest isotope, which is uranium-238. But one thing to pay attention to is look at the last column. That's the abundance. As it turns out, that uranium-235, even though it gives off the most heat, there isn't a lot of it. In fact, it's really, really rare. If you look at something like potassium-40, it gives off about 1/20th the heat of uranium-235, but it's super abundant. And the neat thing about potassium-40 is that it's just the right size that it likes to fit into lots of our minerals that are common in volcanic rocks, like the feldspars. The feldspars love this stuff. Fits in there really nice. So this is an element that's pretty abundant, gives off a fair bit of heat, and is available to heat up rock and eventually melt it. So there's different elements that produce heat. Some produce a lot of heat, but there's not much of them. Others don't produce as much heat, but there's quite a bit of it. So overall, potassium, thorium, uranium, they provide a fair bit of heat within our Earth as well. So we get lots of heat from the original accretion of material back when the Earth first formed as a planet. And then we have additional heat that comes in all the time as these radioactive elements release heat. And if you look at the half-life, you can see that the half-lives are ridiculously long. Billions to tens of billions of years. So what that means is there's still a lot of this stuff. The Earth's only 4.6 billion years old. Most of the half-lives are longer than this. So that means we have more than half of the original material from when the Earth first started. So this is sort of a long-term way of producing heat that will be around for a lot longer. We talked about this just a minute ago, that back when the Earth first formed as a planet, it probably heated up enough so that everything melted. The heaviest elements, the densest elements, migrated towards the core. So we have a nickel-iron core. And then the lighter materials went to the top. Lots of silica. It's much less dense than the nickel and iron. So we have this process of differentiation where we have core formation, crust formation, and the mantle is made of kind of the intermediate density materials. How do we know we have a metal core? We've never been there. We've never even been to the mantle. How do we know we have a metal core? Any idea? Okay, we do know that the Earth is a magnet, right? And one of the ways that you can initiate a magnetic field is to have moving metals. So that tells us that we probably have some moving metals somewhere in the Earth, so that makes sense that perhaps we have moving metals in the core that creating our Earth's magnetic field. Anything else? How do we know it's nickel iron? It could be a lot of different metals that could create that, right?
Don't we study how like the PNS waves, how they move through?
Okay, so we have earthquakes that send PNS waves through the planet, right? S waves do not travel through liquids. So if we have a big earthquake on this side of the Earth, what we've noticed is that the other side of the Earth doesn't get any S waves. And that's because there's probably a molten layer within the Earth that's dampening them out. And in fact, you can look at where the S waves do occur and get an idea of just how big that is. So we have earthquakes that give us some idea of the state of matter, and the speeds are determined by the density. And we know nickel and iron is about the right density to match the earthquake patterns that we have. We also have meteorites. And a lot of the meteorites we get are from planets that either came together and exploded or didn't quite form, and we get lots of nickel-iron meteors, probably from the asteroid belt, where we had a planet that may have come together and just couldn't stay together. And finally, we know the gravitational strength of the Earth's gravity field. And once you know that, then you know the mass of the Earth. We know the density of the rocks in the outer part, and we know that there has to be something really, really dense inside. And in fact, you can do the math and figure out that you need material that's 11 grams per cubic centimeter to give the Earth the right weight. And that just happens to be what nickel and iron weigh. So we have all this indirect evidence of what the inside of the Earth is like. Okay, another source of heat, and it's probably not a big deal here on Earth, but it is a big deal in some other places, especially one of the moons of Jupiter called Io, is tidal energy. Jupiter's a big planet. It's got lots of mass, so it has really big tides. And Io gets squished by this tidal squeezing. Here on Earth, our moon revolves around the Earth, and it's enough to warp the water bodies on the surface, and we get tides along coastlines. Well, it's so strong on Jupiter that it actually changes the shape of the moon. It's so strong that it squishes the moon. And as this squeezing occurs, there's lots of friction inside the Earth, or inside that moon, as the moon adjusts to the new shape. And this interior kneading is enough to create enough heat for volcanism. And in fact, this moon of Jupiter called Io is the most volcanically intense body in the whole solar system. It's got dozens of volcanoes that just erupt constantly. It's an impressive place. I'll try to show you some images of it in coming weeks. Okay, so far we have several sources for heating. We've got leftover heat from when the Earth first formed as a planet. We have heat from the decay of radioactive materials. And we have some of this tidal energy, this tidal kneading. Now the Earth is cooling off. In fact, its average temperature is dropping about 100 degrees C per billion years. So it's about 400 degrees cooler than when it first formed as a planet. Heat is being liberated, escaping from the Earth's surface constantly. So the Earth is cooling off, but it's, on our time scale, it's not very significant. So if we look at our nearby planetary neighbors, if we look at Mars, it doesn't appear as though Mars is volcanically active. It doesn't appear as though the moon is volcanically active. It doesn't appear as though Mercury is volcanically active. We're not completely sure about Venus. We haven't explored Venus enough and sent enough return missions to Venus to look for changes at some of the volcanoes. Some people suggest that, yeah, maybe there could be activity there, maybe not. But Earth is really active. We have lots of volcanoes. So what's different about the Earth than these other planets that gives us so much volcanism? Well, let's start with Mars. Mars is a small planet, right? Why might Mars not have volcanism? What's that? It did. Mars has the biggest volcanoes in the solar system, by far. Olympus Mons is 90,000 feet high. If you put it on Earth, it would cover Colorado completely. That's just one volcano on this tiny planet. But there's no evidence that there's been any volcanism in the last 2 billion years. So it looks like Mars is dead. Why would Mars be dead? It released its small. It's a much tinier planet, so it had much less heat to begin with. Mars probably just lost its heat, much like the moon. The moon probably lost its heat as well. Mercury is tiny. It lost its heat. But now you got the Earth and Venus, and they're about the same size. We know Earth has lots of volcanoes that are active. We're not sure if anything on Venus is at all. So if we go through these, the moon and the plate tectonics are one thing that differentiates Earth from Venus. We know Earth has plate tectonics. We're pretty sure Venus does not. And the Earth has a moon, which might give some sort of tidal heating, and Venus does not. So plate tectonics seems to be pretty important in terms of creating volcanoes here on Earth. The other thing that's different about the Earth and the other planets is the original chemistry. When these planets were first put together 4.6 billion years ago, each planet ended up with a slightly different chemistry based on how far away from the sun the planets were. We just happened to be at the right distance away from the sun that we ended up with lots of water. Venus didn't get much water. Mars didn't get much water. We were in that perfect band where water was stable, so Earth got lots of water. So we have water not only in our oceans, but we have a lot of water in minerals in the Earth as well. We have lots of hydrous minerals. And that could be a reason why we have more volcanism here as well. It's something we'll talk about next week, how water affects the melting point of different rocks. So the Earth is different from the neighbors in that it has a moon, maybe some tidal heating, plate tectonics, which we'll talk about a lot over the next few weeks, and we got a lot of water. So we have lots of water in our minerals. That changes the way they melt. Again, something we'll talk about coming up.